Hello and welcome. It's time for some stoichiometry. So we're in chapter 4 of Zumdahl, and what we need to focus with and on now is solutions. And the key with solutions is we got to remember we're dealing with water. Okay, um, water on Earth is our predominating solvent. So we need to consider the how and why behind that. The shape of water being what it is, we have a bent structure, which is a derivative of the tetrahedral structure in a molecule. We have what you don't see, two pairs of electrons on the central atom that force this bond angle a little bit more narrow than 109.5 that we would expect to about 105. It varies from source to source, so don't fall in love with memorizing a bond angle. Know that, though, it's slightly less than what you would expect for tetrahedral, so less than 109.5. But what other mysteries come from water because of this? Well, all of them. Because the electrons aren't shared evenly, we have um, difference in electronegativity among these two atoms. In other words, oxygen is more attractive to electrons than hydrogen. It's got many more protons in the nucleus, and therefore is more attractive to any surrounding electrons than hydrogen can be. So attractive that we have a greater electron density in the molecule around the oxygen than hydrogen, which explains this net negative charge in this zone of the molecule. We also don't forget two pairs of electrons on the central atom that aren't being shared. So moving through, I've given you three different molecular representations here. One's the one from the previous page, one with electron density coming in bands where the increasingly darkness of the molecule gives you an idea of where the electron density is. Then a sort of a shade map, we're seeing more and more of these now that kind of indicate with the shades of gray the depth of electron density throughout the molecule, where the dark black is where you see most of the electrons aggregated. And so you see this density around the oxygen that's not there around the hydrogen. This accounts for all that polarity in the molecule, the net positive charge on the hydrogen wings and the net negative charge on the oxygen. So we talked about polarity, and this is why water is such a wonderful solvent for things that are even the slightest bit polar and ionic. It doesn't dissolve things that are nonpolar, so calling it the universal solvent is kind of untrue, but it's a really good solvent, so we'll take that. The electron poor-end hydrogen attracts anions and electron-rich portions of polar molecules. The electron-rich end, the oxygen, attracts cations and electron-poor regions of polar molecules. So think about that when we look out orients. Water is responsible for taking an ionic crystal and taking it into bits, and what we call ionizing it. That's provided that it's something the water can dissolve. Water needs to be able to dissolve this ionic molecule, or ionic compound, pardon me, and if it can dissolve it, it will form ions. This process is called hydration, and water uses its polar parts to do this. Um, Keep in mind that hydration causes ionic compounds to dissolve and ionize. It also can dissolve polar covalent compounds, but remember, polar covalent don't ionize, they simply dissolve. Water does not dissolve non-polar covalent substances. There's not enough attraction between the molecules for there to be any action, so no action takes place. It's kind of just nothing happens. Um, Hydration, we have an intact crystal surrounded by water molecules. What we see happening is the water molecules attack the cations with their oxygen end. The oxygen, remember, the electron dense portion goes after the positively charged cations, surrounds them completely, and just escorts them into the solution. Because you got to remember, there's water molecules all around that are interacting with these water molecules that have this cation in their hands. Contrast that with what you see with the anion, and you see the hydrogen ends of the water molecules uh, grabbing onto the anion. The electron poor regions are grabbing onto the negatively charged anion. Again, 360 degrees, you have water molecules grabbing these ions and just interacting back with the solution. So this is a representation of what we'd expect to happen when potassium chloride were dissolved. So what I'm going to do real quick is kind of put it back together a little bit. Here's potassium chloride. What we would expect to happen is the water molecules' negative parts will grab onto the potassium in 3 dimensions. This is 2-dimensional, so don't get too upset with the ugliness of it. Contrast that with the other ion, the anion, being associated with the hydrogen ends of the water molecule, and you see what's sort of like hydration. And once this happens, the water molecules are just going to be interacting with other water molecules. So that ion is now, or sorry, that formula unit of potassium chloride from the crystal is now in solution. Solutions are homogeneous mixtures. You should discern one phase. In a solution, the solute dissolves in the solvent. Just because something dissolved does not mean it ionizes. It should be ionic to ionize. If the solute ionizes in the solution, electricity can be conducted, and the solute is said to be an electrolyte. This includes acids. Strong acids ionize completely and therefore will conduct electricity, even though an acid typically are covalently bonded and there's no metals present. If the solute ionizes 100% or near 100%, we call it a strong electrolyte, and we'll get into that in a bit. Lesser ionization occurs with weak electrolytes. This is the notion of electrolyte behavior comes from Svante Arrhenius, who determined that the extent to which a solution can conduct an electrical current depends directly on the number of ions present. We look at the more ions in the solution, the more electricity it will conduct, and we can actually quantitatively measure conductivity with several different units and tools. Solubility we represent graphically, numerically with a mass per given volume of solvent or number of moles in a given volume of solution. This is what we're used to, a solubility curve set with solubility expressed in grams solute per 100 grams of water, and since we know the density of water is 1, we can extrapolate to a volume. Strong electrolytes are soluble salts, and we'll use our solubility tables for that. Get used to a few of the rules here in a bit. Strong acids ionize completely, hydrochloric, hydrobromic, hydroiodic, then nitric, sulfuric, and perchloric, with chloric acid in some lists will appear in this, and there's others that appear in the list too, but generally speaking, those 6 in black are most common, with chloric bringing up the rear. Sometimes even nitric's is mentioned to be a not completely strong acid, but we won't really worry about that in AP Chem. So what does complete ionization look like? Imagine you have hydrochloric acid molecules here. Okay, these are usually going to come in gas form if they're intact. Hydrochloric acid, we can keep it in gas form pretty easily. The way we make hydrochloric acid is to bubble that molecule through. So when exposed to water, the water molecules will ionize the hydrogen and the chloride from one another and make them part of the solution. Now, if you ever see hydrochloric acid in the lab at full 12 molar, you'll notice it fumes constantly, forming the hydrochloric acid gas. So it will join the air pretty easily. The Arrhenius theory of acids basically states that a substance that produces hydrogen ions in water solution is an acid. The one fundamental flaw here is that acids don't always appear in aqueous solutions, so we can't restrict them to that definition. Otherwise, though, this is a pretty useful definition for our purposes. We'll get into a better definition later. Strong bases ionize completely. They contain hydroxide. If you were to taste them, they would feel bitter, or they would taste bitter and have a slippery feel. Two most common, sodium hydroxide, potassium hydroxide, that are both soluble and strong. Most of the strong bases are not terribly soluble in water. Weak electrolytes ionize incompletely. And when you take acetic acid and place it in water, say for example in a solution of vinegar, what you would find is that acetic acid would ionize only a small degree. You would have mostly intact acid. So if you were to draw a solution containing molecules of acetic acid, you would expect it to look like this. Mostly intact molecules with maybe one of them ionized. You wouldn't need to have to draw the exact molecule shape, just the idea that you would have one anion and cation, anion and hydrogen ion, and the rest intact acid. Ammonia, being a weak base, does not ionize completely either. When ammonia is passed through water, only a bit of it ionizes to form ammonium and hydroxide. Most of it stays in gas form. We measure molarity in terms of moles of solute per liter of solution. This is the way we work in chemistry with molarity typically. We also will see millimolar occasionally when dealing with very small molarities, and that will make our numbers a little more relatable. Moles per milliliter of moles solute per milliliter of solution. But we'll cross that bridge when we come to it. So a simple molarity question: calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 ml solution. Delicately read that and note that you're putting a salt in enough water to make 125, not 25 grams solute plus 125 mils. That would lead to that small volume that this would occupy would not allow that to stay 125. So the way we do it is we take that mass and we figure out how many moles it is. The way we do the math is we take the mass, we use the molar mass to convert to moles, and then divide by the volume we expect to make. The actual technique we'll explain in a moment. The next question: how many grams of sodium sulfate are required to make 300 mils of a 0.5 molar solution? This is taking advantage of the molarity formula to determine a volume. So we start with this volume we were given, then we use the molarity to get to the number of moles in the solution, and then we can easily convert to the molar mass, and that gives us the mass of solute required to do this. What volume of 1 molar potassium nitrate must be diluted with water to prepare 500 mils of 0.25 molar potassium nitrate? This is a simple dilution question. There's no real balanced chemical reaction to worry about here. All we're doing is taking water and adding it to a sample. The only difference from the left side of the equation to the right is added water. Some volume of water was added to the original sample in order to create a new solution, molarity, and volume. So the way it gets handled is the M1V1, M2V2, okay? And solving for that unknown volume, we would say 125 mils was our original volume, and then we, to make our 500 mil volume. But the interesting piece there is that we look at this and see, oh, well then how much water must have been added? Well, if our initial volume was 125 and our final volume was 500, then the added volume must have been 375. So we added 365 milliliters of water. This equation only gets used for dilution. Don't use it for chemical reactions, for acid base, for anything else ever. We have strategies for handling those types of questions more functionally. Using this for other purposes leads to failure. Do not do it. This is what I was talking about with building an aqueous solution. In order to build a properly quantified molar solution of a sample, we put the weight amount of solute into our volumetric flask. We pay attention to our volume marker and understand what the symbology means and the volume expresses in terms of significant digits. We then add a quantity of water sufficient to dissolve the solute, and then we swirl, 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 swirl the bottle. Once we feel that our solute is completely dissolved in the solvent, we will fill our solution, we will fill the bottle to the fill line. And if we do that successfully, we can expect the molarity of the solution to be exactly as we calculated. Then again, there are ways we can test that, and we'll learn about that soon too. That's the end of the first video. This we'll continue with the next video. I hope you've taken high quality notes, and if you have any questions, please see me with them at our next encounter.